Okay, so we've been talking about work energy theorem, okay, for the last week or so here. So now we're going to do a lab where we're going to do some work, no pun intended, we're actually doing like real physical work as well as like work, okay? So we're going to be doing that, and we're going to be finding out how we can calculate work. Now, we already know essentially how to calculate work. We know that work is a change in energy, right? So if we have the initial and final energies, we can calculate it that way. Or we can multiply what together? Force and distance, right? So we have a couple of ways to calculate work, right? And one has its place and the other has its place, and those places are sometimes the same and sometimes different, right? We have to look at in this lab which one's the most appropriate way to calculate work. All right, so that's the problem we're investigating. How do we determine the amount of work done on an object? Okay, for this lab, okay, here's how this lab is going to work. I'm going to be a little bit more cryptic this time in terms of the variables, so you're going to want to listen carefully. I'm not outright telling you anything this time. All right, so we've got this situation. We're going to be putting a rubber band across the legs of two desks. Okay, we're going to stretch that rubber band. Okay, and the two things we're going to be measuring are, we're going to measure distance and we're going to measure force. Now, the way this lab is going to work is this. Once I have the rubber band put across the two legs, I am going to choose several distances to which I'm going to pull the rubber band. Those distances are 2 centimeters, 4 centimeters, 6 centimeters, 8, 10, and 12. Sorry, I didn't have 12 on there, but that'll fill up your chart if you see your chart there. However, in your chart, they need to be in meters. So that would be 0.02, 0.04, etc. Okay? So I'm going to choose those distances. I'm going to pull back the rubber band using a spring scale to those distances. The spring scale will measure the force that is needed to pull the rubber band back to those chosen distances. Okay. Now, a spring scale. A couple of things that I need to watch for throughout the lab. Okay. The first thing is that you're going to need to be in like groups of at least 3, probably 4, because 2 people, their job is going to be to sit in the desks while this lab is going on, because the desks can't move during the lab. If they move, the tension that is initially in this rubber band will change. And then essentially I'm dealing with a different rubber band. And I want to deal only with the same rubber band in every trial. That would also mean that I probably need to be careful if I break this rubber band, and it happens occasionally during the lab. What do I have to do? I have to start over again with a new rubber band. Okay? Supposedly these are all number 33 rubber bands. I have no idea what that means, but apparently they're all the same, but I don't know about that. Okay? I can't be 100% sure. Okay? So if, like this one here, for example, has a notch in it already, okay, I put this thing under any kind of tension, it's for sure going to snap. Okay? And there's a few that have little imperfections in them like that, and that might happen. Okay? Other things that I want to be watching for are how I do the measurements. Okay? You can see from this diagram that the ruler is going to start right between the two desks. Okay? So if I'm looking at this from above, the ruler is going to be right halfway between the front of the rubber band and the back of the rubber band. Okay? That's where the 0 mark is going to be. When I'm pulling this back, I need to have someone who's looking at it straight down from above. That way I don't bring any angular stuff into my measurement. It's called parallax, okay? And I don't want to bring in any parallax and cause any error, okay, when I'm doing my measurement. So I want to have one person who's standing right over top, okay? Everybody with me so far? All right, so I've given you a few now. If you're paying attention really carefully, you've got 4 out of the, sorry, you've got 4 out of the 5 now, okay? You have to think up another one. probably a controlled variable. Okay, anything that affects the tension in this rubber band has to be controlled. Okay, anything that could affect the tension, the initial tension that is in the rubber band. All right, so the other piece of equipment that we're going to be using are these spring scales. Okay, we had a bit of an issue with these spring scales when we first moved into this school and we had ordered all our new equipment. Mr. Dickey and I were unloading all the boxes full of physics equipment. It was like Christmas in August. Okay, we had all this new stuff. And we pulled out the box that had the spring scales in it. And we're like, oh, sweet. They were exactly the ones we ordered because, of course, we were looking at the boxes. And on the box is a picture of exactly what we ordered. Problem is, what's in every single box is not what's on the box. So the ones that are on the box have one side that is force in newtons and the other side is mass in grams. The ones we have mass in grams and mass in ounces. So, we called Northwest Scientific and said, hey, you sent us the wrong stuff. What do we do about, getting these back to you so we can get the right things? They said, no, we sent you the right stuff. And we said, no, you sent us the right boxes, not the right stuff in the boxes. They said, no, you're not getting a refund or an exchange. You got what you ordered. We've never ordered from Northwest Scientific again. If you ever get into business customer service, the customer's always right, especially when they are right. These are not the right scales. Okay. Anyway, it's not that big a deal. We'll be able to convert the grams into force pretty easily. Okay. That's just my story. Another life lesson for you. You got a life lesson yesterday. This is like your week of life lessons. Okay. All right. Customer's always right. Okay. So that's going to be the procedure. Okay. We're going to draw back the rubber band. Okay. Using the spring scale. All right. So you'll have the rubber bands. Okay. Between the two desks. The spring scale has a hook on it. Get both sides of the rubber band on the hook, okay? And then just pull, and you see that it moves the spring scale, okay? When there's no tension, that's where it sits. When there is tension, it pulls like this, okay? So we're going to use the distances that are listed there. One thing you do need to check on your spring scale before you start is that it's actually at 0 when there's nothing pulling on it, because this thing can adjust, okay? The meter thing in there, it can adjust, and you want it sitting so that that thing is on 0 when you start. Okay, a lot of people miss that part and then they get kind of weird data. Okay, so just make sure of that. Okay, for our hypothesis then, okay, if and then statements. Okay, in the if part, I would say that's where you should tell me what work is. Okay, give me kind of a definition of what work is in the if part of your hypothesis. Okay, and what I mean there is what's the definition of work, not what's the formula to calculate it. All right, so in other words, I don't want to see work is force times, if work is force times distance. I don't want to see that in the if part. Tell me what work is. Okay, maybe how you know it's been done or something like that as part of your description of work. The and part just describes the experiment. Okay, tell us what we're doing here with the rubber band and the spring scale and the ruler. The then part should talk about how you calculate work. Okay, then work can be calculated by doing this. Okay, and like I said, we've been doing that kind of all week, so you should be able to have a formula there, especially considering the two things we're measuring in this lab. It should be pretty obvious what formula we're looking for in order to calculate work. All right, so when we do this graph, okay, you're going to be filling in your chart that's going to have the distances on one side and the forces on the other. All right. When you have those, you're going to create this graph of force versus distance. Obviously, these are the two very important variables in this experiment. The graph here may help you decide which one's which. Okay. So you're going to make a graph. It's going to look something like that. It's not going to look exactly like that, but it'll look something like that. Okay, plot it in Google Sheets, same as we always do. Okay, so just take that chart, put it in Google Sheets, and you're good. All right, with that graph, okay, what you're going to do, and you're going to paste that graph in here. Okay, what you're going to do is the calculation listed here in number 1. You're going to calculate the area under the line. Okay, now there's a couple of ways that your graph might look. Okay, your graph could look kind of like your need for speed graph did. It could look like this, depending on your data. Okay, or it could also look like this. Okay? Either way, you guys know how to calculate the area underneath the line. You have to get your shapes. Okay? It's just in this graph, it doesn't represent displacement. It's going to represent something else. Okay? To figure out what it does represent, look at what's on the graph. You've got distance here and force here. And if you're calculating the area, think about what you're doing with those two numbers in order to calculate the area. Okay, that'll give you a hint as to what the area represents, which is all what question number 2 in the analysis is asking. Okay, what does the area under a force distance graph represent? How do you know? All right, so you should tell me what it represents and give me an explanation. Don't just write, it's this. Okay, that's not going to be good enough. Tell me why you think that is. Talk a little bit about your calculation. Talk a little bit about the kind of stuff that you did in there. All right. Then you got your conclusion, so restate your hypothesis, explain why you accept or reject it. In there, you should probably talk again about, what work is and if you were able to calculate it at any point during the lab, okay, stuff like that. What did you do to get it? Okay, those can be your things that can help you to accept or reject your hypothesis, right? Sources of error and suggested improvements, how many of those? 2, okay? And then you don't have to do the class discussion. We'll talk about those when you submit the labs, and I've marked them. Okay, so when we set up this lab, okay, we want to push 2 desks together. Okay, so put them about like this, okay, side by side, and you're going to put the rubber band around the top of the feet. Okay, so the feet, okay, are these things here. The rubber band should go there. Okay, not up on the shaft of the leg. Okay, down in there, right, on both desks. So the 2 front legs that be side by side. Then pull the desks apart until it's just taut. Okay, if it's slack, then the desks aren't far enough apart. I also don't want it to start like this. Okay, if it starts like that, you're going to stretch this beyond its normal elastic range. All right, if you watch, like when I'm stretching this, right now it stretches really easily, but when I get to a certain length, it stops being really elastic, right? And I'm pulling a lot harder to get it to stretch, and it's going to snap pretty quick. Okay, so we want to be utilizing as much as possible the true elastic range of the rubber band. You'll know if you go beyond that elastic range because you'll get these nice points like this that are very linear, and then you'll get like that. You'll get 2 that are like, or 1, your last one might be out a bit. That just means you're kind of beyond the normal elastic range of the rubber band. It's not the end of the world, okay? But if you've got like 5 points that look like that, then you need to redo it, okay? Everybody with me there? So 2 people sitting in desks to keep them from moving. Make sure that you do the whole lab, nobody moves, okay? Because if it does, it's going to mess up your results. Okay, and then 1 person who's doing the measuring, okay, and 1 person who's doing like the pulling. Make sure, as in the diagram here, that the hook on your spring scale catches both sides of the rubber band, not just one side of the rubber band. Okay, we need to be pulling on both. Everyone follow there. Okay, I'm making Maddie nervous. Okay, there are 2 different sets of scales in the box there. You want the kind that have 2,000 written on the top. They're the 2,000 gram ones. They pull harder. Okay, if you grab a 500 gram one, you'll max out the scale before you get to the last number, right? So make sure you grab the 2,000 gram ones. And as we said before, these don't show force. Okay, they show mass, and that's no good to us. So what we have to do is divide whatever it is in grams by 100. And that will give us the force in newtons. It's actually 98.1, but just for the sake of being quick, we're going to divide by 100 instead. Okay, so divide the mass in grams by 100, and you'll have the force in newtons, and that's what you're graphing, is force versus distance. Okay, all right, questions on what we're doing here? Okay, so get yourself into groups and get started. Due date for this, guys, is next Wednesday.